Okay, so we're looking at functions, graphs, and matrices, Math 158. These are the notes on section 1.1, functions from the numerical, algebraic, and graphical viewpoints. Okay, so we're going to look at functions. What is a function? We're used to seeing equations. Okay, and again, note guide, blank note guide was also posted on Blackboard, so if you want to get a copy of this to follow along, you can. So I'm going to be looking at, we have the equation y equals 2x minus 8. We're used to seeing y equals 2x minus 8 is an equation, right? If x equals 2, y equals negative 4. If x equals 5, y equals 2, okay? Now we're going to talk about a function. We're going to use function notation. So instead of writing y equals, we're going to write f of x equals 2x minus 8. And what we say is that y is a function of x. What do we mean by function notation? We kind of get into some of the stricter algebra, the higher level algebra. When we start talking about function notation, we're talking about a calculus type application for when and if we ever get there. What it means for something to be a function is a rule. A function is not just any equation, but a function is a rule that associates each input with exactly one output. I kind of thinking of a job. If you have a job and you work for a salary and you get paid $12 an hour. For each hour you work, you get paid $12. The amount of money that you earn, we're not talking about you get to keep after taxes, but the amount of money that you earn is a function of, is a result of the number of hours that you work. So if you make $12 an hour, then f of x is equal to 12x. If you work 5 hours, you will make 12 times 5 or $60. F of 10 would be 120. If you work 10 hours, you make $120. The amount of money that you earn is a function of the number of hours you work. For each input, there is exactly one output. Okay? So we can come up with equations, examples of equations that are not functions, but for right now, we're going to talk about just equations that are functions. For each input, there's only one output. When we get into conversation of functions, we often get into the conversation of domain and range. And I can hear a lot of algebra students who start to, groan, oh, domain and range. I hate domain and range. I don't understand domain and range. One of the things, and I'm going to go a little off script over here, one of the things I think that makes domain and range difficult is that early on in an algebra experience, algebra 1, algebra 2, those types of scenarios, we talk about linear equations or linear functions. F of x equals 3x plus 5. Or we talk about quadratic functions. F of x equals x squared plus 4. We talked about those last time. Or we talk about exponential functions. F of x equals 3 to the x. And we will talk about those in this course. You may or may not have seen those in the past. But we talk about the domain. And in an algebra setting, we talk about the domain is the set of x, the set of values that x can equal. So if I look at this value of f of x equals 3x plus 5, what can x be? Well, x can be 2, it can be 5, it can be 3. Well, x can be anything. So the domain is the set of all x values such that x is a real number. The domain is all real numbers. F of x equals x squared plus 4. What's the domain? The domain is the set of all x values such that x is any real number. What can x be in the exponential function? It can be anything. So the domain is the set of all x values such that x is some real number. Stop me, back up, hear what I'm saying, because I'm writing that for a little notation check there. The domain is the set of all x values such that, that's pretty much template. And then what is it that x can be or x cannot be? X in all of these cases can be any real, is a real number. Okay? And what happens, I think, is we're in this situation where what can x be? X can be anything, x can be anything. I tend to explain domain and range in the context of food allergies. Okay, and I often tell a story. Suppose that I'm going to have a bunch of students over. Last person's house, you want to go to his mind, but I have a bunch of students over, and I'm going to serve some food. I'm going to do some grilling. We're going to do some preparing, and we're going to have some food. I'm going to say, what I want to do in preparation for having students over is I want to make sure that I don't serve foods, or I only serve foods that students can eat. Okay. And so what I want you to do is I want you to start making a list of all foods that you can safely eat. Well, this can be tedious. I can eat pizza. I can eat cheeseburgers. I can eat chicken. I can eat. And you start making a list of all the foods that you can eat. That gets a little exhausted. At some point, there's going to be some student who's going to raise their hand and say, I have a question. Wouldn't it be easier if we made a list of all the foods that we cannot eat? Okay, so my wife has a dairy allergy and a gluten allergy, and so she would make a list and she would say, I can eat all foods except for dairy. I can eat all foods except for gluten. Okay, so this starts to make more sense. I can eat everything except for. And if I think of this food analogy comparison, there are some major food allergies that we deal with, right? Nut allergies, gluten, dairy, soy, some of those things. I'm actually in a class recently, I said it might be something as silly as I'm allergic to bananas, and I had a student said, hey, I'm allergic to bananas. That's kind of a little lesser known one. The primary ones are your gluten, your dairy, your nuts. Enough, nutrition conversation, food conversation. I'm getting hungry. When it comes to math, we talk about domain. There are a couple of what I call major domain allergies, making air quotes, domain allergies. What are those scenarios? Here are the major ones, okay? First of all, understand you cannot divide by 0. It's impossible to divide by 0, okay? So if I've got a function f of x equals 3x plus 2 divided by x minus 5. In my numerator, x can be anything. That's a linear function, very similar to this guy here, where x can be anything. But my denominator has a problem. That denominator cannot equal 0. You can't divide by 0. Here's a little quick explanation into that. What's 15 divided by 3? Well, 15 divided by 3 is 5, and we're all very good at that. Why? You can give me, well, because 3 goes into 15 5 times. If I divide this, you're using division to define division. The reason that 15 divided by 3 is 5 is because 3 times 5 is 15. 10 divided by 2 is 5 because 2 times 5 is 10. 20 divided by 2 is 10 because 2 times 10 is 20. You got it? So here's a question for you. What is 0 divided by 6? Well, 0 divided by 6 is 0 because 6 times 0 is equal to 0. But what is 6 divided by 0? Suppose that 6 divided by 0 is some number n. 0 times n would have to equal 6. What number can I multiply by 0 to get 6? Well, nothing. This is why this is undefined. The reason that 6 divided by 0 is undefined is because there is no number n that can be multiplied by 0 to get 6. Nothing works. It's undefined. So if I look all the way back, over here, x minus 5 cannot be 0 because I can't have a 0 in the denominator. Therefore, add 5, x cannot be 5. That's my domain. X can be anything except it can't be. I can eat anything except I can't eat dairy. I can eat anything, but I can't eat peanuts. My domain is the set of all x values such that x is not 5. This implies that x can be anything except for x can't be 5. Okay? Another parenthetical thought here. Suppose f of x equals 3x plus 6 divided by 2x minus 3. What is it that x can be? Well, x can be anything except for, domain allergy number 1, I cannot get a 0 in the denominator. Therefore, my denominator, 2x minus 3, cannot be 0. Solving for x, so 2x cannot be 3, so x cannot be 3 halves. X can be anything except it can't be 3 halves. So my domain is the set of all x values as long as x is not 3 halves. And there's the domain. It implies x can be anything except for what it can't be. So let's look at bullet number 1 here. What's the domain of g of x if g of x equals 3x minus 1 over 2x plus 6? Well, 2x plus 6, that denominator, cannot equal 0. Therefore, 2x cannot equal negative 3. Therefore, x cannot equal negative 3 halves. So my domain is the set of all x values such that, or as long as, x is not negative 3 halves. Okay, that was crazy. There's domain allergy number 1. Domain allergy number 2 is the radical here. Okay. Underneath that radical, where that 5x minus 10 is, that number cannot be negative. You cannot find the square root of a negative number. The value that's underneath the radical, that I don't know what I did here. Okay, this happens from time to time, so please bear with me. I'm getting better at these videos, but I'm not perfect yet. Okay, so f of x equals the square root of 5x minus 10. This value, that 5x minus 10 that's underneath the radical, cannot be negative. It has to be greater than or equal to 0. It can equal 0. The square root of 0 is 0. 0 times 0 is 0. So the square root of 0 is 0. It can be positive, any positive number. It just can't be negative. So 5x minus 10 has got to be greater than or equal to 0. So I'm going to add 10. So 5x is greater than or equal to 10. Divide both sides by 5. And x has got to be greater than or equal to 2. So my domain is the set of all x values such that, or as long as, x is greater than or equal to 2. So there's my domain. Okay, so we have our two major domain allergies where we cannot get a 0 in the denominator, we cannot have a negative under the radical. Okay. Now, a comment here about domain, natural domain compared to restricted domain. Okay, I like to use an example like this, right? So let's suppose that we have a concave down parabola that looks like this, and this represents the height of an object after I throw it. So here's time t equals 0, and here's time t equals 4. So whatever object I'm throwing, it takes 2 seconds for this object to reach its maximum height, 4 seconds to reach the ground. Now, as just a natural function, this can go down to negative infinity, it can go down to negative infinity, but if I'm talking about throwing an object, this part over here and this part over here, those two parts don't really make sense. Because the object, I can't talk about throwing the object before I threw it, and I can't talk about the height of the object under the ground. So although for a concave down parabola, the domain would be all real numbers, okay, the natural domain would be the set of all x values as long as x is a real number. In this case, though, where I've thrown the ball up, and the object from t equals 0, it goes up and it reaches its maximum height after 2 seconds, and it reaches it back to the ground, it's going to stop. This reality is only going to exist as long as x is between 0 and 4. So although we have the natural domain for the function, we have the restricted domain where the function is relevant, where it matters, where it exists, where it tracks the movement of an object. Okay. So when I look at functions, I can look at functions 3 different ways. Okay. One, I can look at the function numerically. Okay. So this table shows the number of Facebook members each year since since the start of 2004. I will tell you, I am not at all. This is just a personal commentary. I'm not a fan of social media. I'm much more of a fan of face-to-face interaction. I don't measure my number of friends by the number of people that like my comments on Facebook. I'm not on Twitter. I don't do Snapchat, Instagram, all those things. I'm an old guy. You know, I'm almost 55 years old at this point, and I much prefer social interaction. Well, that's just my comment, right? That's just every once in a while you'll get these glimmers into me, right? And what am I like, and how do I think, and all that kind of stuff. In any case, Facebook, right? So if I look at the number of of Facebook members each year since the start of 2004. So 0 is the year 2004. 1 is 1 year after 2004, so that would be 2005. Okay, 2005, 2006. Really fun thing. This will come up later in the course as well. Is the fun question to ask is what year is it, right? So in 2004, Facebook had 0 members. 1 year later, they had 1 million members. After 2 years, they had 5.5. 3 years, they had 12 million users. And so I see the function here, which tracks the number of Facebook users each year since 2004, numerically, or in a table, the number of Facebook users. It's a table of values, T-chart, if you will. If I graph that data on a coordinate plane, 0 years, there's 0 users. After 1 year, there are 1 million users. I think it said after 2 years, we had 5.5 million users. After 3 years, we're at 12 million. 4 million. After 4 years, we're at 5.5. And you see graphically the growth in the number of Facebook users, right? Functions can be displayed numerically in a table, graphically on a graph. Functions can also be expressed algebraically or in an equation. So like f of x equals x squared algebraically. Okay, so we can express functions in a table numerically, graphically in a graph, algebraically. In this course, much more of an algebraic expression, we're going to use functions. We're going to use the graphs of the functions to talk about them, but we're also going to work with them algebraically. Okay, so at this point, let's look at evaluating functions, right? So suppose f of x equals 3x plus 5. How would I find f of 2? Well, notice instead of f of x, I'm finding f of 2. So instead of x, I'm going to have a 2. That would be 3 times 2 plus 5. 6 plus 5 is 11. So f of 2 would equal 11. F of 0, notice I replaced the x with a 0, so I'm going to replace the x with a 0. Okay, so to find f of 2, I replace the x with 2. To find f of 0, I replace the x with 0. To find f of 3, I'm going to replace f of negative 3, I'm going to replace the x with negative 3. To find f of t, I'm going to replace the x with t. Okay, now I can evaluate these, right? 3 times 0 is 0 plus 5 is 5. So f of 0 is 5. 3 times negative 3 is negative 9 plus 5 is negative 4. So f of negative 3 is negative 4. Now in this case, f of t equals 3t plus 5. 3t, 3 times t is 3t plus 5. So f of t is 3t plus 5. And it's pretty much just a change in the variable in that case. Number E or part E and part F are a little bit different, right? So I have f of x, which was my 3x plus 5, and I'm just going to add h to it. So I have 3x plus 5 plus h. F of x plus h is a little bit different. Notice that instead of the x here, we have x plus h. So instead of x, we replace the x with x plus h. Okay. Now I'm not going to expect you to, I don't think, to distribute this, but 3 times x is 3x. 3 times h is 3h. And then, whoops, nope, I don't do that, plus 5. So I can expand that out if I would like. Okay. So number 2 is the same thing, it's just with a quadratic. Okay. To find f of 2, I'm going to replace the x with a 2. 2 squared is 4, times 2 is 8. 4 times 2 is 8 minus 5. 16 minus 5 is 11. F of 2 is 11. To find f of 0, I'm going to replace x with 0. 0 squared is 0, times 2 is 0. 4 times 0 is 0, minus 5, and that's just negative 5. F of 0 is negative 5. Okay, so to find f of 2, we replace x with 2. To find f of 0, we replace x with 0. To find f of negative 3, we're going to replace the x with negative 3. Negative 3 squared is 9, times 2 is 18. 4 times negative 3 is negative 12, minus 5. 18 minus 12 is 6, minus 5 is 1. So f of negative 3 is 1. F of t, we're going to replace the x's with t's. So we have 2t squared plus 4t minus 5. So f of t is equal to 2t squared plus 4t minus 5. And you really should answer these with an equation. I'm going to expect that you do. That's like using a complete sentence. Okay. F of x plus h, again, is simply f of x, which was the 2x squared plus 4x minus 5. That's f of x plus h. That's simple. F of x plus h, notice that we have 2x squared plus 4 times x minus 5. But we're going to replace the x with x plus h. Now, if you want to, you can go ahead and expand that. I don't need you to. And why do I keep jumping around? Okay. You can expand that if you want to. Quite honestly, I don't need you to. So you can just leave that f of x plus h. At this point, you don't need to expand it. You will need to be able to. You do want to make sure that you know how and that you can. But I don't need you to at this point. Okay, so okay, it is true that all functions are equations, but not all equations are functions. Right? Suppose I say y squared equals x. If y squared equals x, let x be 16. Y squared equals 16. Y could either be a positive 4 or y could be a negative 4. So for the one value 16, I get multiple y values. That is not a function. Okay, so just be careful. Just because you have an equation doesn't mean you have a function. A function is a special type of equation. Another type of function that I want to talk about just briefly is what's called a piecewise function. Okay, a piecewise function follows different functions for different values of x. Okay, without getting too much down this road, our tax code in the United States is a piecewise function. If you make under this amount of money, you pay this much of tax. If you make more money, you pay a certain percentage tax on the first amount and a different percentage tax on the next amount. So you have different things, and we're not going to get into the U.S. tax code. Okay, but I have a piecewise function. In this piecewise function, what I want you to understand is that in f of x, I use the function 2x minus 3 if I have x values less than or equal to 2. If my x values are greater than 2, I use the other piece of the function. So let's look at a couple of examples here. Let's find f of 0. 0 is less than 2. So f of 0 is 2 times 0 minus 3, or negative 3. What about f of 5? F of 5, well, 5 is bigger than 2. So f of 5 is going to be 5 squared plus 1, which is 25 plus 1, or 26. Notice that the piece, right, piecewise function, the piece of the function 2x minus 3 or x squared plus 1 that I use is dictated by whether the x value is less than or equal to 2 or greater than 2. Okay, so let's suppose that I want to find f of 2. Less than or equal to. So for f of 2, it's going to be 2 times 2 minus 3. 4 minus 3 is 1. Okay, so use a different piece of the function depending on the value of x. Okay. Vertical line test is something a lot of students have seen. If every vertical line drawn on a graph intersects a graph in at most one place, then the graph is the graph of a function. Otherwise, the graph is not the graph of a function. Now, this is a lot easier for me to do if I'm standing at a board, at a whiteboard, right? But let's suppose I have this function. I have this graph. Is this a function? Okay, got a little carried away there. Is this a function? Well, is it possible for me to draw a vertical line through this function, through this graph, that intersects it in more than one place? It's not possible, therefore this is a function. Compare that to this graph. Is it possible for me to draw a vertical line that will go through this graph in more than one place? Notice that this vertical line, it is possible to draw a vertical line through the graph that intersects in more than one place. So this is not a function. Because for each value of x, there can be only one value for y. For this value of x right here, I could have a value of y here, here, here. Not a function. Okay. What about a circle? Is a circle, that's a pretty ugly circle. That's a better circle. Is a circle a function? Well, is it possible for me to draw a vertical line that will intersect the x-axis? Intersect the x-axis. Is it possible to draw a vertical line that will intersect the graph in more than one place? Yes. This vertical line crosses here as well as here, so this is not a function. Okay, and that's called a vertical line test. Please understand something, by the way. This graph here is a function because for each value of x, there's only one value for y. The test is not what causes it to be a function. It's how I know. Okay, now, just a quick run through, and I'm not going to fully develop this yet, at least not in this section. We're going to look at some of these functions, right? These are common functions you might see. A linear function. The graph is a line. A quadratic function is going to give us a parabola. It's quadratic. A cubic function, the highest degree term is a 3 there. That's a function that's going to look something like this. Those are polynomial functions. They're all functions. Polynomials are always functions. Okay, polynomial looks like this. It looks really kind of scary. We'll come back to those. Okay, I'll visit that at another day when we get really into polynomials. Okay. An exponential function, the graph of an exponential function is going to look like this. Notice that that will pass the vertical line test. For each value of x, there's only one value of y. A logarithmic function will look like that. And that is a function. Rational functions, it's a function divided by a function, kind of like the first ones we did, where f of x was 3x plus 2 over x minus 5. Okay, rational functions look like that. I'm not going to show you the graph today. Not going to worry about that. An absolute value function, the graph of an absolute value function looks like this. A square root function will look like that. Notice that they all pass the vertical line test. Those are all types of functions. Okay, so we're going to revisit some of those types of functions as we go through the course. But what you want to have today is an understanding of what a function is. What is it that makes something a function? For each value of x, there's only one value for y. You want to be able to evaluate the functions. Okay, so again, there are problems assigned in WebAssign, so make sure that you do those. Okay, in order to practice, it's also part of your grade.